Welcome to Wireless Fundamentals, Session 2, Modern Standards and Modulation. Now that we understand the early standards, it is easy to understand more modern standards like 802.11n and 802.11ac. These standards provide much higher performance due to features like channel bonding, MIMO, spatial streaming, and short guard. We'll then wrap this up with a discussion about specific aspects of RF waveforms, which will help us to understand how digital data is sent along these analog radio waves. Let's get started. The 802.11n standard gained traction around 2009-2010. Engineers developed new techniques, pushing data rates up to 150, 300, and even 450 megabits per second. These techniques were applied to both the 2.4 and 5 gigahertz bands. Don't forget our earlier discussion about the difference between the theoretical data rates you see listed here versus actual, real-world throughput. The same estimations apply. If you are connected at, say, a data rate of 150 megabits per second, your actual real-world throughput will probably be around 70 to 80 megabits per second. Currently, the 802.11ac standard continues to gain a following. The first wave of products offer potential speeds of up to 1.3 gigabits per second. The second wave of 802.11ac will offer speeds of up to 2.34 gigabits per second. This technology is only viable on the 5 gigahertz band. It relies heavily on a bundling of multiple channels together into a single communications path to increase bandwidth. Since the 2.4 gigahertz band only has 3 non-overlapping channels, this channel bonding technique is not practical in this band for an enterprise. Let's talk about this feature. With 802.11n, you can combine two adjacent 20 megahertz channels into a single 40 megahertz channel. Bandwidth for a particular WLAN is more than doubled because the guard band between the two 20 megahertz channels can be removed when they are bonded. This guard band is used to prevent interference between channels. This bonding is what enables us to achieve data rates of up to 450 megabits per second. Channel bonding is typically used in the 5 gigahertz frequency band because it has more non-overlapping channels. Since the 2.4 gigahertz frequency band has only 3 non-overlapping 20 megahertz channels, bonding two 20 megahertz channels leaves only one non-overlapping channel available. This is why channel bonding is not practical for the 2.4 gigahertz band. Hey, doesn't this remind you of configuring port aggregation on Ethernet switches? This can enable you to combine 2 or more 1 gigabit per second Ethernet ports into a single aggregate, giving 2, 4, or even 8 gigabits per second. So that's an analogy. Think of the 802.11n standard as only being able to bundle 2 channels together. The latest standard, 802.11ac, can do even more. 802.11ac's first wave can achieve up to 80 megahertz wide channel paths and up to 1.3 gigabit per second data rate. 802.11ac second wave products become more widespread as of mid-late 2015 with up to 160 megahertz wide channels. You may have noticed that many 802.11a, B, G based radios have 2 antennas. This visual cue has misled people to point one antenna in one direction and the other antenna in another direction, thinking they'll cover more space. Not only is this untrue, but it reduces the effectiveness of the 2 antennas. With 802.11a, B, G radios, only one antenna is ever used for any given transmission. When a client transmits, part of the signal takes a direct path to an AP. A portion of the signal may bounce off of a metallic object, arriving at the AP antenna a few microseconds later. Since these waves are out of phase, they distort and detract from each other. This is called multipath distortion and is the reason for having multiple antennas. The AP intelligently detects this condition and uses the other antenna. If those 2 or 3 signals are converging at the left side antenna, they are therefore not converging anywhere else. 802.11n technology converts this liability into an asset. Multiple input, multiple output, or MIMO, means the AP can use multiple antennas at the same time. An 802.11n device can be classified as having 2x2 MIMO. This means that it has 2 transmit antennae and 2 receive antennae. A 2x3 device has 2 transmit and 3 receive antennas. And you can guess what a 3x3 MIMO means, huh? MIMO can be leveraged in 2 key ways to provide superior performance. Beamforming is a feature that sends multiple streams of the same data from its transmitting antenna array. The transmitter adjusts the magnitude and phase of each transmitter to optimize how they are received by the client. This feature is especially useful when the AP has multiple antennae, but the client has only one. With spatial streaming, the data to be transmitted is split up, with different portions transmitted out multiple antennae. Each spatial stream takes a unique path to the client. This is most useful when both AP and client have true MIMO capabilities. Each spatial stream provides transmission rates of up to 150 megabits per second. So APs that support 2 spatial streams, like the MSM 430 and 425, can provide data rates of up to 300 megabits per second. APs with 3 spatial streams, like the MSM 460 and 466, can provide up to 450 megabits per second. The latest 802.11ac capable APs, like the HP 560, can do even more with the same 3 streams, giving us up to 1.3 gigabit per second data rates. Look at this chart for a moment. Do you notice that all of these APs support 802.11abg in addition to 802.11n or AC? As typical, an 802.11n or AC capable radio is downward compatible with the older technology. The same protection mechanisms we discussed for 802.11b and G also enable compatibility between 802.11a, N, and AC, as well as for 802.11b, G, and N. But hey, what if you don't want older 802.11b clients on your network? Good question. You will soon learn how to configure our systems to control power, channels, and speeds supported. We have complete control over this. For now, let's continue on with our discussion of 802.11n and AC. HP's patented short-guard feature improves performance for multicast transmissions. It does this by enabling users to leverage the higher throughput available in 802.11n and AC for multicast traffic. Other vendors still rely on slower 802.11abg speeds for this traffic. Let's take an opportunity to check our knowledge of some key concepts from the material covered so far. Submit your answers to the following questions and use the Continue button to move forward.
This is really helping. Thanks, Vivek. But I would appreciate a deeper understanding of how RF works. Why is 802.11b so much slower than other standards? Also, I'm not very clear on concepts and terms like frequency and those phase relationships you mentioned earlier.
You ask good questions. A firm grasp of these concepts will really help you understand what's going on here at Paradise. Let's get a little more clarity on how RF works. It's all about waves. RF energy can be compared to sound and light. It travels in waves. The properties of these waves determine how they are perceived and how they can be utilized to represent data. One such property is frequency. This relates to how often a wave begins at some point, rises to a crest, falls to a valley, and then returns to that same point. The blue wave shown starts at a 0 on the x-axis, has a single peak, an ensuing valley, and returns to 0. This is a single cycle, and since it happened in 1 second, we say that the frequency is 1 cycle per second, or 1 Hertz, named after Heinrich Rudolf Hertz. He proved the existence of electromagnetic waves, as predicted by Maxwell's equations. The red wave shown has 2 peaks in the same amount of time, and this is referred to as a 2 Hertz signal. If the wave cycles up and down 2.4 billion times in 1 second, it is a 2.4 gigahertz wave. The amplitude of a signal is related to its strength or size. The blue wave shown has a relatively high amplitude as compared to the red wave. When you increase the volume on your television, you are increasing the amplitude of the signal that is sent to the speakers. The amplifiers of various audio systems can be compared by how much power they have, in units of measure called watts. Similarly, you can adjust the power output of your APs to control how far the signal travels.
Hey Vivek, wait a minute. Maybe we can increase the power of our APs and help the users that are getting a poor signal. How do I do that?
Hey, now you're thinking. I'm glad you keep applying these concepts to the real world. You have good instincts. But don't forget our earlier discussion about blinding white light in a reflective room. You'll also be learning several more reasons why increasing AP power often makes things worse. For now, let's continue our discussion of RF waveforms. Another way to consider RF signals is the phase relationship between them. The figure shows 2 signals that are identical. You can barely see the red wave behind the blue one. That is because they are perfectly aligned or in phase. The blue signal is not shifted in relation to the red signal. Here you can see the blue signal is now shifted 90 degrees as compared to the red signal. And now it is 180 degrees out of phase. This is an exact opposite or mirror image of the red signal. By the way, noise-canceling headsets work on this principle. A microphone picks up offending noise and sends it to a tiny processor, which creates an equal but opposite signal 180 degrees out of phase. This tends to cancel out the signal. So Vivek, I guess waves are a little out of phase cancel each other out a little bit, like what happens with multipath distortion we talked about. You are absolutely correct on that. Keep thinking. And now look, the 2 signals are 270 degrees out of phase. I know, this is getting a bit deep, but stay with me. This will actually help us to understand how data is represented over our WLAN, and why 802.11g and A are faster than B, and why some users get faster performance than others. Let's talk about modulation. Modulation is simply another term used about varying or modifying some aspect of a waveform. Transmitters can vary or modulate some aspect of a wave, such as its amplitude, frequency, or phase. A receiver can then key off of that aspect to interpret these variations as binary ones and zeros. The figure depicts a fictitious protocol that uses amplitude modulation or amplitude shift keying. During the first time period, the amplitude of the signal is relatively low. Some standard could be developed that interprets a low amplitude as a binary 1. In the next time slot, the same signal has a larger amplitude, which could be interpreted as a binary 0. Of course, this representation is arbitrary. You could create a standard where a low amplitude is interpreted as a binary 0 and a high amplitude is a 1. As long as everyone uses the same standard, We can use this scheme to represent binary data. The figure represents frequency modulation or shift keying. In the first time slot, the signal has a relatively high frequency, which could be interpreted as a binary 1. The frequency is slower in the second time slot, representing a binary 0. You can also key off of a shift in the phase of a signal. Assume that in the first time slot, the wave continued or flowed normally from the previous time slot, with a 0-degree phase shift. However, as the wave transitioned from the first to second time slot, it did not continue without shifting. Instead, the phase shifted 180 degrees. So there are only two phases used in this scheme. If one time slot is 0 degrees out of phase with the previous one, this can represent a binary 1. If the signal is 180 degrees out of phase, this can represent a binary 0. Since there are two phases in use, this is called binary phase shift keying. This relatively simple waveform is what 802.11b uses to achieve a 1 megabit per second data rate. This signal can travel a relatively long distance, degrading significantly without negative effect. An AP and client could still discern between a 1 and a 0 because the waveforms are so distinct. They are the opposite of each other. What if we used 4 different phases: 0, 90, 180, and 270 degrees? With double the phase differences, we can represent twice the data. This is called quadrature phase shift keying, or QPSK. This is what 802.11b uses for 2 megabits per second. It combines this technique with something called complementary code keying to achieve its 5.5 and 11 megabit per second data rates. Just do an internet search on CCK if you want to know more. I wouldn't bother. It is sufficient to know that it increases the complexity of the waveform in order to represent more data in the same amount of time. Taking this even further, imagine that we vary two aspects of the wave, both phase and amplitude. We can again double the amount of binary data encoded in a given time slot. Low amplitude in phase can represent a binary 0000. Low amplitude 90-degree shift equals 0001. Higher amplitude with a 180-degree shift can equal 0100, and so on. Now imagine using 4 phase shifts with 16 different amplitude levels. That's called 16 QAM, or even 64 QAM. This is what 802.11n uses to get its highest data rates. 802.11ac expands this even further by using up to 256 QAM.
Hey Vivek, I get it. So because high-speed modulations are more complex, the variations in waveforms are more subtle. So if you are close to an AP, the very strong, clear signal will enable the use of these methods without creating errors. So you might connect at 150 megabits per second using 64 QAM. But as you walk away from an AP, the signal degrades, becoming more blurry, I guess you could say. This creates errors which the AP and client detect, and so they automatically rate shift down to a simpler waveform such as 16 QAM. This enables you to continue communications reliably, but at a slower rate.
That's right. I'm so glad you keep applying this theoretical knowledge to a real-world scenario. That's the reason we need to understand all of this, and it will remain important as we move to ever more advanced concepts, such as how to optimally place APs to ensure end-user satisfaction, and how to prevent a few slow talkers from impeding the performance of the fast talkers on a WLAN. Let's take an opportunity to check our knowledge of some key concepts from the material covered so far. Submit your answers to the following questions and use the Continue button to move forward.
Okay, I understand about RF waves now, but don't they require some type of antenna? Also, I notice that sometimes I see antennas attached to an AP and sometimes I don't. Why is that? Do I need to worry about antennas and how they work?
Good question. But we should probably end this session and take a break. In the next session, you'll learn the important aspects of how antennae are used to propagate RF waves. This should help you to make decisions about which AP and antenna combination is best suited to a given scenario.